This is FE Peer Review. The date is August 17th, 2021. Kyle Adams and Gravity, or In Praise of Ignorance. This video is in response to one specific point in Kyle Adams' video called Gravitational Force. My purpose here is not to debunk or correct Kyle Adams' ideas on gravity. Mr. Sensible did an excellent job of dissecting the video in its entirety, and I encourage people to check out Mr. Sensible if you haven't already. My purpose is to confront Adams' attempts to hide behind a false humility of proclaiming ignorance to actually hide from learning. At the end of this video, I will read to you Einstein's own words, his own thoughts on Newton and the growth of knowledge.
What is gravity?
I have no idea. Okay, next question.
Wow.
No, here's the difference. We can describe gravity.
Okay.
We can say what it does to other things. We can measure it, predict with it. But when you start asking, like, what it is, I don't know.
With that, while it may surprise you, I actually agree with him. Was Newton right, or was Einstein right? Were they both wrong? Or were they both right? I don't know. That is a mystery we are still trying to figure out, just like the rest of the world.
There is nothing wrong with admitting ignorance. In fact, it is often a positive thing, as it opens the path to learning. Over the course of getting my bachelor's degree and 2 master's degrees, one of which was in structural engineering, one thing became very clear to me. The more I learned, the wider the landscape of knowledge became, the more there was to learn. Nature's complexity increases as you delve into it. The more I learned, the more I understood how much I did not know. It was a humbling and liberating experience, and it could never have happened if I had been ashamed or inhibited in any way in acknowledging my ignorance. But hiding behind ignorance to avoid learning is self-destructive. Adams uses Tyson's comments as a justification for brushing aside what Tyson does know and what he, Adams, can learn from him and other more advanced scientists. Adams even has the gall and pride to place his ignorance side by side with Newton and Einstein. Newton, Einstein, Tyson, Adams. At least one of these names, arguably 2, do not belong next to Newton or Einstein. I'd like to remind Adams and others that Tyson, as smart as he is fundamentally a science communicator and a generalist. For any specific subject such as gravity that Tyson talks about, there are many specialized scientists who know vastly more about the subject than him. Tyson, as a communicator, is great at bringing knowledge to the general public, but don't mistake what he has to say as the most advanced knowledge on the subject. So, Adams acknowledges there's a lot he doesn't know about gravity. That's great. And it's true that Tyson and others will admit there is plenty that mainstream scientists don't know about gravity too. But there is a difference. I ask you, Kyle Adams, what do you know about gravity? What has your knowledge about gravity enabled you to do? Here are some of the things humanities scientists have been able to do with the current knowledge of gravity. Let's start by looking at mapping of gravity variations around the planet. What you see here is the NASA Earth Observatory website and an article about a project called GOCE, Gravity Recovery and Climate Experiment, and it was a joint program between NASA and the German Aerospace Center. You've got this beautiful map here which shows the Earth, and the color coding represents gravity anomaly, a slight increase or a slight decrease in gravity. It's measured in milligauss, and it goes from plus 60 to minus 60, with plus 60 being a slight increase, which you see in areas where there are mountains, also in here, and minus 60 being a decrease. Milligauss, by the way, it says down here in the note, 1 milligauss is approximately 1/millionth of the average strength of Earth's gravity field. So back in 2003, when this project started, they were measuring the gravity field to the 1/1,000,000th. Here's a Wikipedia article about the same mission, and it had a interesting tidbit on measurements, how this measuring was done. 2 satellites were used to do this project, and they were identical satellites in polar orbit. They were launched to be 220 kilometers apart, following the same path, and they had a microwave relay between them that measured the distance between them. The ranging system, it says here, the ranging system is sensitive enough to detect separation changes as small as 10 micrometers, approximately 1/10 the width of a human hair, over a distance of 220 kilometers. So as these 2 satellites orbited the Earth, one following the other, by the way, they were called Tom and Jerry. So when Jerry would be running away from Tom and passing over an area of higher gravity, that higher gravity would cause Jerry to speed up a little bit, and the distance between the 2 satellites would increase a little bit. And then as they continued orbiting, Tom would pass that same point, and he would speed up due to the high gravity in that spot, closing the gap back to where it had been. So this gap, which was increasing and decreasing, was being measured, and the changes were how they were able to determine the changes in the gravitational field of Earth. Not bad for people who don't know what gravity is. This is from the NASA website, and these are some nice visualizations they created from their data. There are going to be links in the description to all the stuff you see on the screen here today, pointing out that mountain ranges increase the field because the mountains are more dense than the areas where there's more water. Here you see the Mariana Trench reducing the field. For the next example, we will look at the European Space Agency and something called the GOCE satellite, GOCE. It stands for Gravity Field and Steady State Ocean Circulation Explorer. And it was a satellite that went up for 4 years, 2009 to 2013. It was a single satellite, not the Tom and Jerry approach, and it measured using accelerometers. It had 6 accelerometers, 3-axis accelerometers that were so finely tuned that they were able to measure these changes in gravitational field. Now the satellite flew very low, 200 and some miles above the surface of the Earth. So they weren't able to keep it up long, only 4 years, but they got a lot of data about Earth's gravitational field from that satellite as well, and they used that to refine the geoid, which is the basis for GPS systems and so forth. So again, not bad for people who don't know what gravity is. Here we see the European Space Agency website with an article about the mission. And this page explains a bit about the accelerometer that was used, the measuring equipment, the accelerometers and other things that was used. To find out more, they have some nice information on their equipment. 3-axis diagonal gradiometer, 3 pairs of electrostatic servo-controlled accelerometers. Not bad for people who don't know what gravity is. What about LIGO? You may have heard of LIGO, the Laser Interferometer Gravitational Wave Observatory. It's an observatory. That means it observes things. However, it's not like our typical observatory, which has a telescope or a radioscope or something inside. It's observing gravitational waves, and it does that with several facilities around the world, comparing information received. Now, this is way beyond me. This is not my expertise, but it's measuring gravitational waves, and it's succeeding. This nice article here explains the basics of what the LIGO is all about. And the LIGO detectors, it said the lessons learned during initial LIGO's operations, let me highlight that, led to a complete redesign of LIGO's instruments, which were rebuilt between 2010 and 2014. This redesign and subsequent improvements will ultimately make LIGO's interferometers 10 times more sensitive than their initial incarnation. This deeper search for gravitational waves began in September 2015, and within days, LIGO's advanced detectors achieved what LIGO could not accomplish in 8 years of operation before that. LIGO's interferometer made the world's first detection of gravitational waves, heralding a new era in astronomical exploration. The waves detected by LIGO on that day were generated by two black holes colliding and merging into one, nearly 1.3 billion light years away. Pretty cool for people who don't know what gravity is. But how about using gravity? What can we use it with? What can we do with it? Well, here was a nice little video I found on YouTube that's about the Mariner 10 NASA mission back in, when was that? I think 1973. And it was the first NASA mission to use what they call a gravitational assist or a slingshot to accelerate a spacecraft. Now, I believe the Soviets had actually beaten NASA to that and to use the gravitational assist on one of their missions earlier than that, but I don't have the details on that. So this nice little video here explains a bit of the history of Mariner 10. I think I'll just put the link in the description. I won't go ahead and play it here. But it's a good simple description of how Mariner 10 slingshot its way around Venus to increase its momentum. NASA has a nice page on how to do a gravity assist. Link in the description. It explains how as the craft approaches, as a spacecraft, let's take a look at this image here. As the spacecraft approaches a planet, the gravitational attraction of that planet draws the craft towards the planet, and that means it's accelerating towards the planet and speeding up. However, if everything's done correctly, it will miss the planet. It will be falling towards it, but it will miss it, and in gaining that speed, it will maintain a large part of that speed as it leaves the influence of that planet, and thereby speeding up, it will also change its course. The Cassini mission was another great example of how to use our knowledge of gravity to slingshot a spacecraft. The problem we had with Cassini was, here's this diagram that shows the sun, where I'm circling my mouse, and Earth is a blue dot here. We could build a spacecraft, a rocket powerful enough to leave Earth and leave the influence of Earth's mass. But we don't have the technology to build a rocket that's powerful enough to do that and also escape the influence of the sun's mass. We could launch a rocket off Earth, but it's going to eventually get pulled back into the sun and not make it out to Saturn. So if you want to get to Saturn with the current technology, you've got to find another way. And the way that they found back in 1999 was to do 2 flybys of Venus. Each time it flew past Venus, it was speeding up. A third flyby took it past Earth and sent it on its course out towards Jupiter. When it got to Jupiter, there was a bunch of neat scientific experiments going on, but it was also, yet again, slingshotting and using the mass of Jupiter to gain momentum and carry it on to Saturn. So there you go. Gravity assist. They call it gravity assist for a reason, because it uses gravity. The Juno mission did a cool thing when they managed to break free from Earth's gravitational influence and slingshot around a bit as well. They got some neat imagery of Earth and Moon from quite far away, and they made a film out of it. It says on the page here, during the flyby of Earth, timing was everything. Juno was traveling about twice as fast as a typical satellite, and the spacecraft itself was spinning at 2 revolutions per minute. To assemble a movie that wouldn't make viewers dizzy, the Star Tracker had to capture a frame each time the camera was facing Earth at exactly the right instant. The frames were sent to Earth where they were processed into video format. I encourage you to look at the video of this flyby. So each time that every 30 seconds, as the spacecraft kind of flipped around and was facing the Earth again, it took another picture. And then they assembled all these pictures as it flew past Earth and Moon. Here's just a bit of that video. I'm not going to play the whole thing. I don't want to run into some kind of rights issues, but I'll play a little bit of it with the sound turned off. That's just a preview. There's a lot more, and it's really cool. So check it out. It's in the description. So that's some of what humanities scientists have been able to do with our limited understanding of gravity. Kyle Adams, I have a question for you. What have you been able to do with your limited understanding of gravity? These missions I mentioned are, of course, NASA missions. And I know how you, Kyle, like to hide behind innuendo and baseless suggestions of conspiracy and lies on the part of NASA as a way of not facing what humanity has been accomplishing for generations. Unfortunately for you, that's the best you've got. Faced with the hard reality that we have photographed the Earth from space, that we have used our knowledge of gravity to slingshot spacecraft into the outer solar system, that we have mapped Earth's gravitational field to the milligal using satellites orbiting our poles. Faced with all that, all you can do is cry hoax and conspiracy as you desperately try to preserve your ignorance. Why do I even bother with you, Kyle Adams? Because you would pass yourself off as a teacher. Because you would spread your ignorance. Ignorance reduces human freedom. It imprisons the mind. It's true to say that ignorance even kills. That's why I bother. I'd like to end this video by reading Einstein's eulogy to Isaac Newton on the occasion of the 200th anniversary of Isaac Newton's death. It was a letter that he wrote to the Royal Society in honor of that occasion. More than any other people, you Englishmen have carefully cultivated the bond of tradition and preserved the living and conscious continuity of successive generations. You have in this way endowed with vitality and reality the distinctive soul of your people and the soaring soul of humanity. You have now assembled in Grantham in order to stretch out a hand to transcendent genius across the chasm of time, and to breathe the air of the precincts where he conceived the fundamental notions of mechanics and of physical causality. All who share humbly in pondering over the secret of physical events are with you in spirit and join in the admiration and love that binds us to Newton. What has happened since Newton in theoretical physics is the organic development of his ideas. Force became independent reality to Faraday, Maxwell, and Lorentz, and then went over into the conception of the field. The partial differential equation has taken the place of the ordinary differential equation used by Newton to express causality. Newton's absolute and fixed space has been converted by the theory of relativity into a physically vital frame. It is only in the quantum theory that Newton's differential method becomes inadequate, and indeed strict causality fails us. But the last word has not yet been said. May the spirit of Newton's methods give us the power to restore unison between physical reality and the profoundest characteristic of Newton's teaching, strict causality. Thank you for joining me today. If you enjoyed this, please do click that like button and share this with your friends. And as you all know, I always enjoy a good comment. Have a great day. Bye-bye.